Welcome to Teolumen Insights, where we reveal the hidden forces that shape the way you live and show you how to use them to create real transformation and supercharge your health, mindset, and daily life. Here are your hosts, Emma Greenwood and Nathan Sinclair.
Welcome back to Teolumen Insights. I'm Nathan Sinclair, and today we're diving into the world of tachyons.
Tachyons.
These hypothetical particles that always travel faster than light.
Always faster than light.
Joining me is our expert guide, Emma Greenwood. We've got a fascinating mix of scientific papers, research articles, and even some science fiction to explore how these particles have really captured the imagination.
It's true. They really challenge our fundamental understanding of physics. We're going to unpack some mind-bending concepts today. Causality, time travel, even touching on the nature of reality itself.
Okay, so first things first, the term tachyon. It wasn't always the go-to name for these particles.
Right.
Our sources mention physicist Sudarshan Deshpande and Misra, who first proposed faster-than-light particles, calling them metaparticles.
Yeah, their work was groundbreaking, but it was physicist Gerald Feinberg who really brought the term tachyon into the spotlight back in 1967.
1967.
Yeah, he had this unique approach extending Einstein's theory of special relativity to include particles that always exceed the speed of light.
Hold on a second. Extending special relativity. That sounds like a pretty difficult task.
Yeah.
How did Feinberg even begin to tackle that?
Well, his work is based on something called extended relativity.
Extended relativity.
Yeah, this framework uses the same fundamental postulates as special relativity.
Okay.
The laws of physics are the same for all observers in uniform motion, and the speed of light in a vacuum is constant for all observers. The twist is that Feinberg applied these postulates to the realm of superluminal speeds.
So instead of saying nothing can travel faster than light, Feinberg's framework asked, what if something always travels faster than light?
Exactly.
Yeah.
What would that look like? It was a thought experiment with enormous implications.
Yeah.
And those implications lead us to some of the most intriguing and challenging aspects of tachyon theory.
We're talking things like paradoxes and violations of causality, right? Those seem like pretty significant challenges to our understanding of how the universe works.
Absolutely. One of the biggest hurdles tachyons present is to our understanding of causality, the idea that a cause must always precede its effect.
Right.
If something can travel faster than light, it could theoretically arrive before it departed,
Right.
creating some serious logical knots.
Like that classic grandfather paradox.
Yeah.
If you could travel back in time and prevent your grandparents from meeting, would you even exist?
Precisely. That's a perfect example of the kind of conundrums tachyons introduce.
Yeah.
Our sources delve into a similar paradox called the tachyonic paradox to illustrate these causality issues.
All right, walk me through this tachyonic paradox. How does it work?
Okay, so imagine two spaceships,
Oh, okay.
each controlled by robots programmed to act to tachyonic signals under specific conditions.
Okay.
This setup ultimately leads to a situation where one spaceship receives a signal from its own future, causing it to self-destruct before it even sends the signal, creating a mind-boggling contradiction.
It's almost like a self-fulfilling prophecy gone wrong. A spaceship is destroyed because it received a signal from itself being destroyed, but it couldn't have sent that signal if it was already destroyed.
Exactly. It perfectly highlights the potential for time paradoxes when you bring faster-than-light travel and communication into the picture.
So we've got these tachyons zipping around, potentially messing with the past and future. How does this all fit into the broader context of special and general relativity?
Oh,
There must be some major theoretical issues at play here.
There are, and our sources go into some detail about the mathematical tools and concepts physicists have developed to try and address these issues.
Give us the highlights.
Yeah.
What are some of the key things that stand out?
One concept is switching.
Etching.
This is where a tachyon can appear to travel backward in time from the perspective of certain observers.
Okay.
It has to do with how different reference frames perceive the sequence of events when something is moving faster than light.
So it's not that the tachyon is actually reversing time. It's more that our perception of its movement through time gets skewed.
That's a good way to put it. Imagine a film reel playing backward. The events are the same, just the order is reversed.
Our sources also mention something called the Eigen convention and the I rule. Can you unpack those for us? What are they all about?
Essentially, they're mathematical tools designed to make sure calculations are consistent when dealing with tachyons.
Okay.
The Eigen convention deals with the appearance of imaginary numbers in the equations used to describe tachyonic motion.
Right.
The Chi rule relates to the concept of switching and ensures that quantities like energy and momentum are conserved even when a tachyon appears to be moving backward in time.
It sounds like these tools are a way to patch up the holes that tachyons poke in traditional physics equations, kind of like mathematical bandages.
That's a good analogy. It really emphasizes how much tachyons make us rethink our assumptions about how the universe operates.
Speaking of rethinking assumptions, our sources mention another intriguing point. To conserve energy and momentum, tachyons sometimes require the use of negative energy values in specific situations.
It's a mind-bending concept. It's like saying you can have less than 0 apples.
But from a mathematical perspective, in the context of tachyonic theory, it seems to make sense.
It does, and it leads to some profound questions about the very nature of energy. Does negative energy have a physical meaning? If so, what are the implications?
So many questions to consider. We also need to talk about superluminal Lorentz transformations, or SLTs.
Right, SLTs are modified versions of the Lorentz transformations used in special relativity.
Okay.
In special relativity, Lorentz transformations connect the space-time coordinates of events as seen by observers in different inertial frames. But with SLTs, these transformations are adapted for superluminal speeds.
So it's like taking the mathematical language of special relativity and tweaking it to describe this bizarre world of tachyons.
Precisely. It's an attempt to bridge the gap between our current understanding of physics and the mind-boggling possibilities that tachyons introduce.
Now, before we get too lost in the theoretical weeds, I want to shift gears for a moment. One of our sources highlights a real-world application of the tachyon concept, a bioinformatics tool also called Tachyon, used to speed up sequence searches in those massive protein databases.
It's a great example of how even purely theoretical concepts can inspire practical tools.
Yeah.
And the name tachyon is very fitting, considering its purpose is to make things go much faster.
How much faster are we talking? Give us some numbers.
Hold on tight. We're talking approximately 200 times faster than BLAST, a widely used sequence search tool.
Wow, that's an incredible leap forward in speed. So essentially, Tachyon, the bioinformatics tool, borrows inspiration from tachyons, the hypothetical particles, to achieve superspeed in the world of protein analysis.
Exactly. Even if tachyons turn out to be just a theoretical concept, their impact on scientific progress is undeniable.
All right, let's get back to the theoretical side of things.
Yeah.
We need to talk about neutrinos. These particles have always been a bit of an enigma, haven't they?
They have. And one of the most interesting possibilities our sources bring up is that some neutrinos might actually be tachyons.
That's an intriguing twist. What kind of evidence supports this idea?
It's mostly circumstantial, but there are several tantalizing clues. For instance, many measurements of neutrino mass have resulted in negative mass squared values, which is a characteristic feature of tachyons.
Wait, negative mass squared? How is that even possible?
It's a bit of a quirk that comes from how mass is defined in the context of special relativity.
Oh.
It doesn't necessarily mean that neutrinos have negative mass in the everyday sense of the word.
Right.
Instead, it indicates that their mass behaves in a very different way compared to ordinary matter.
Our sources also mentioned specific theoretical models that support the idea of tachyonic neutrinos. Could you elaborate on that?
Of course. One example is the 3+3 model,
3+3 model.
which proposes the existence of 3 standard neutrinos and 3 tachyonic neutrinos.
Okay.
This model has been tested against various observational datasets, like those from supernovae, cosmic microwave background radiation, and baryonic acoustic oscillations.
So there's at least some theoretical framework that accommodates tachyonic neutrinos without completely overturning our current understanding of physics.
That's the key point. It's not just some wild idea out there. There's some real mathematical rigor behind it.
Theoretical models are one thing, but what about experimental data? Have scientists actually observed neutrinos moving faster than light?
There have been some interesting hints, but nothing conclusive. One famous example is the opera experiment, which initially seemed to detect superluminal neutrinos. Yeah, however, after further investigation, they discovered that those findings were due to equipment errors.
So close yet so far.
It really highlights the immense difficulty of conducting experiments at the very edge of what's technologically possible. When trying to detect these tiny, subtle effects, we're pushing the boundaries of measurement precision.
Our sources delve into some of the potential consequences if tachyonic neutrinos do exist. What are some of the key takeaways there?
The implications are huge. It could revolutionize our understanding of a vast range of phenomena, from the early universe to the behavior of cosmic rays and even dark matter.
Could you give us some specific examples of how our understanding might be affected?
For example, some scientists suggest that tachyonic neutrinos might play a role in the way dark matter interacts,
Oh.
helping to explain the gravitational effects we observe from this mysterious substance that makes up a significant portion of the universe.
So these faster-than-light neutrinos could be the missing piece in the puzzle of dark matter.
It's certainly a possibility and one that researchers are actively exploring.
Now we need to talk about something called holographic tachyonic dark energy. It sounds like something straight out of science fiction.
It might sound like science fiction, but it's actually a fascinating model that combines the principles of holographic dark energy with the properties of tachyons.
Okay, let's break that down. First of all, what is holographic dark energy?
It's a model that tries to explain the observed accelerated expansion of the universe by relating the energy density of dark energy to the surface area of the observable universe.
Okay.
It draws on the holographic principle from string theory, which suggests that all the information within a region of space is encoded on its boundary.
So in essence, it's like saying the universe is a hologram, and its expansion is driven by the information encoded on its surface.
That's a simplified way of thinking about it. The important thing to remember is that holographic dark energy links the universe's expansion to its information content.
And how do tachyons enter this picture?
In the holographic tachyonic dark energy model, the properties of tachyons, things like their superluminal speed, their potential for time reversal, and their unique relationship with energy and momentum, are incorporated into the equations describing holographic dark energy.
So it's kind of like weaving the weirdness of tachyons into the fabric of holographic dark energy.
That's a pretty accurate description. The idea is to see if this combination can offer a more accurate and comprehensive explanation for the observed characteristics of the universe.
Has this model been tested against any observational data?
It has. Our sources mention that it's been tested against several datasets, including supernovae data, cosmic microwave background measurements, and baryonic acoustic oscillations.
And how do those results look?
It's still early, but the model seems to be showing promise in explaining some of the observed features of the universe, particularly its accelerated expansion.
So holographic tachyonic dark energy is a work in progress, but it's a captivating example of how physicists are pushing the boundaries of our understanding to try and unravel the mysteries of the cosmos.
It reminds us that the universe is full of surprises, and that what we currently know is likely just the tip of the iceberg.
We'll be back after a short break to continue this deep dive.
See you soon. Welcome back to Teolumen Insights. Before the break, we were exploring the potential consequences of tachyonic neutrinos.
It's fascinating to think how these consequences might impact our understanding of big mysteries like dark matter and the evolution of the universe itself.
Let's start with dark matter. It's this mysterious substance that doesn't interact with light,
Right.
which makes it invisible to us. Yet it exerts a gravitational pull and accounts for a significant chunk of the universe's mass.
It's like the invisible scaffolding of the universe, holding galaxies together. We know it's there because of its effects, but we can't directly see it. What's the connection between tachyonic neutrinos and dark matter?
Well, some physicists propose that these superluminal neutrinos might actually interact with dark matter in ways that could explain its gravitational effects.
So these speedy neutrinos could be the key to unlocking the secrets of dark matter. That's a pretty exciting prospect.
It is, and it's something researchers are actively looking into. Our sources mention that certain theoretical models suggest tachyonic neutrinos might act as mediators between dark matter particles. This could influence their distribution and behavior within galaxies and clusters.
So it's like adding a new player to the cosmic game, one that operates by different rules and can change the entire game.
That's a great analogy, and it's not just dark matter that could be affected. Tachyonic neutrinos could also have a big impact on our understanding of the early universe.
Take us back to the Big Bang. How could tachyonic neutrinos have played a role in those early moments?
Well, in the very early universe, everything was incredibly hot and dense.
Right.
Neutrinos, being fundamental particles, were abundant. Now, if some of these neutrinos were actually tachyons, their superluminal speeds and unusual interactions could have had a significant influence on the expansion and cooling of the universe.
So instead of picturing a smooth, uniform expansion from the Big Bang, we might need to imagine a more complex, chaotic scenario with tachyonic neutrinos zipping around, creating ripples and fluctuations in the fabric of space-time.
That's a real possibility, and it's one that could have left observable imprints on the cosmic microwave background radiation, the afterglow of the Big Bang.
So by studying the CMB, scientists might be able to find evidence of these tachyonic shenanigans. That's pretty amazing.
Exactly. The patterns and variations in the CMB could hold clues about the presence and behavior of tachyonic neutrinos in the early universe.
It's not just the early universe, though, right? Our sources mention that tachyonic neutrinos could also be involved in some of the most energetic events in the cosmos, like supernovae.
Absolutely. Supernovae are these colossal explosions that mark the end of a star's life. They release tremendous amounts of energy, and that includes neutrinos. If some of these neutrinos are tachyons, their superluminal speeds could allow them to escape the supernova's core even before the explosion becomes visible to us.
It's like getting a sneak peek at the cosmic fireworks show.
That's a great way to put it. Detecting these early arriving tachyonic neutrinos from supernovae could provide further evidence for their existence and give us valuable insights into the physics of these extreme events.
We've been discussing the potential consequences of tachyonic neutrinos, but we still haven't tackled the big question. How do we know for sure if they even exist?
That's the million-dollar question, and unfortunately there's no easy answer. As we mentioned earlier, the experimental evidence is still inconclusive.
But I imagine scientists aren't giving up. They're still trying to catch these elusive particles in the act, right?
Absolutely. There are ongoing experiments and research efforts dedicated to proving or disproving the existence of tachyonic neutrinos.
What kind of experiments are we talking about?
Many of these experiments focus on measuring the speed of neutrinos with extreme precision.
Okay.
They use sophisticated detectors to capture neutrinos from various sources like the sun nuclear reactors or particle accelerators.
And the challenge is to measure their arrival times accurately enough to determine if they're truly exceeding the speed of light.
Precisely. The differences in arrival times we're talking about are incredibly small, on the order of nanoseconds or even picoseconds.
It's like trying to time a race where the runners are moving at almost the speed of light.
Exactly. It requires incredibly sensitive and precise instruments and very careful analysis to rule out any sources of error or uncertainty.
It's like searching for a needle in a cosmic haystack. But if we find that needle, it would revolutionize our understanding of the universe.
It would be a paradigm shift, forcing us to rewrite the laws of physics as we know them. Now, apart from directly measuring the speed of neutrinos, scientists are also looking for other signs of tachyons.
What kind of signs are they looking for?
One approach is to search for violations of Lorentz invariance, a fundamental principle of special relativity.
Okay.
If tachyons exist, they could potentially break this principle, leading to observable effects.
So it's like looking for cracks in the very foundation of physics.
That's a good way to put it. These cracks could manifest in various ways, like subtle differences in the behavior of particles or variations in the speed of light depending on the direction or energy of the photons.
So it's like searching for tiny glitches in the cosmic matrix.
And these glitches, if found, could provide indirect evidence for the existence of tachyons, even if we can't directly observe them.
So the hunt for tachyons is a multi-pronged effort involving both direct and indirect searches, pushing the limits of our experimental capabilities and theoretical understanding.
That's right. It's a fascinating quest, full of challenges and potential rewards. Even if we don't find conclusive evidence for tachyons, the search itself will undoubtedly lead to new discoveries and insights into the universe.
You know, before we wrap up this deep dive into the world of Tachyons, I want to circle back to something we touched on earlier, holographic tachyonic dark energy.
Right, we were talking about how this model attempts to explain the observed accelerated expansion of the universe by combining the principles of holographic dark energy with the properties of tachyons.
And you explained how it draws on the holographic principle, the idea that the information content of a region of space is encoded on its boundary, like a hologram.
Exactly. Now, in the holographic tachyonic dark energy model, the event horizon of the universe, the boundary beyond which light can no longer reach us, plays a crucial role.
So it's like saying the information about the universe's expansion is encoded on this cosmic horizon.
That's the basic idea. And the model suggests that the properties of tachyons, their superluminal speeds, and their relationship with energy and momentum influence how this information is processed and how it drives the universe's expansion.
Okay, let me try to wrap my head around this. So we've got this cosmic horizon encoded with information about the universe. And tachyons zipping around faster than light somehow tap into this information and use it to fuel the universe's expansion.
It's a complex concept, but that's a good starting point for understanding it.
And you mentioned earlier that this model has been tested against observational data. What did those results tell us?
The model has been compared to several observational data sets, including supernovae data, cosmic microwave background measurements, and baryonic acoustic oscillations.
Those are some of the key tools cosmologists use to study the history and evolution of the universe, right?
That's right. And the holographic tachyonic dark energy model seems to fit reasonably well with these observations.
So it's not just a theoretical fantasy, there's some observational support for it.
There is. But it's important to remember that it's still a relatively new model. More research and analysis are needed to confirm its validity and explore its full implications.
It's like a new piece of the cosmic puzzle, and we're still trying to figure out where it fits.
That's a good analogy. As we gather more data and refine our theoretical models, we'll get a clearer picture of how tachyons, if they exist, could be shaping the destiny of the universe.
Now, before we conclude this deep dive into the world of tachyons, I want to leave our listeners with a thought-provoking question to ponder.
Okay, I'm intrigued. What's the question?
If tachyons could transmit information faster than light, would that revolutionize our understanding of communication and the flow of information in the universe?
That's a fantastic question, and one that takes us beyond physics into the realms of philosophy and information theory.
Imagine a universe where information could travel instantaneously or even backwards in time. It would challenge our very notions of cause and effect, past, present, and future.
It would be a universe where communication could transcend the limits of time and space, where we might be able to receive messages from the future or send messages to the past.
It's a mind-boggling concept, and one that highlights the profound implications of tachyons, even if they remain purely hypothetical.
It's a reminder that the universe is full of mysteries, and that our quest to understand it is an ongoing journey of exploration and discovery.
We've covered a lot of ground today, from the theoretical foundations of tachyons to their potential impact on cosmology, and even their influence on bioinformatics.
It's been a whirlwind tour of some of the most mind-bending concepts in physics.
And I think the key takeaway is that even though tachyons remain hypothetical, their existence or lack thereof has profound implications for our understanding of the universe.
If they do exist, it means we need to rethink some of our most fundamental assumptions about the nature of reality. And even if they don't exist, the very act of exploring their theoretical implications pushes the boundaries of our scientific knowledge and inspires us to think in new and creative ways.
It's a reminder that science is an ongoing process of exploration and discovery. We're constantly pushing the limits of what we know, seeking answers to the most fundamental questions about the universe.
And sometimes the most thought-provoking questions come from the things we don't know, the mysteries that continue to elude us.
Tachyons are a perfect example of that. They represent a realm of possibility that lies beyond our current understanding. And whether or not they turn out to be real, their legacy will undoubtedly continue to inspire scientific inquiry and spark our imaginations for generations to come.
Thanks for joining us on this deep dive into the world of tachyons. We hope you've enjoyed the journey and maybe even had a few mind-bending moments along the way.
Until next time, keep exploring and keep asking those big questions. This has been Teolumen Insights.
See you next time.